So that brings us to a different discussion on gravitational force and weight. All right. So we're going to talk about sort of the difference between weight and mass, which are often in regular life kind of treated the same way. So remember, weight is the magnitude of the force of gravity. That's pretty much just multiply mass times g on Earth, but in general, that's not the way that we do it, okay? So that works on Earth, which fortunately most of our physics problems that we do in this class are set on Earth, so you don't really have to worry about that. But if you're in space or on another planet or anywhere else, you have to know the bigger picture, okay? So that brings us to what I like to call Newton's fourth law, which is the gravitational law, okay? And that's the force of gravity is equal to big G. Remember, we've been dealing with little g. Mass 1 times mass 2 divided by the distance between the center of those masses squared, okay? This reduces to F equals mg, and let me tell you why. So this big G is called the universal gravitational constant. What do we mean by universal? Yeah, in physics, in general, universal means like everywhere and everything, but in physics, it specifically means everywhere in the universe. This is true, okay? And I know it's hard we didn't really check in the other galaxies because nobody's been there, but we actually kind of did because we have telescopes that look really far away and we watch motion of stars and planets and things, and they obey sort of the same rules everywhere. So this is the universal gravitational constant. I forget what the value of this is, but this is if you have any two objects. And honestly, that's as simple as the keys and me, right? If there's actually a gravitational attraction between me and my keys, there's a gravitational attraction between you and the person next to you, okay? It's just very, very small, so small that you don't notice it at all. But if you had a really sensitive measurement device, you could tell by putting masses near each other, they all interact. But mostly you need something really, really, really big. And fortunately for us, the Earth is really, really, really big, has a lot of mass. And so it attracts us rather strongly just because of the sheer amount of mass that it has, okay? So if you wanted to basically what this says is you would be mass 2, Earth would be mass 1, and the distance between your center of mass and the Earth's center of mass is really just the radius of the Earth, because from here to the center of the Earth is a lot bigger than the distance from my belly button to my shoes, okay? So we can kind of neglect that. So in that case, when you plug in radius of the Earth, mass of the Earth, and then any m2 would be this m, this thing right here becomes little g, okay? And g is a gravitational constant, but not a universal one, right? It's the acceleration due to gravity just for Earth and also kind of just for sea level, because if you go up to Everest or if you go down under the ocean, it changes a little bit. Not a lot, but bigger than 10%, okay? So G changes. Also, if you're on the moon, G is completely different, okay? If you're on Mars, G is completely different. So it varies by thing you're standing on, okay? Although if you end up on the moon or Mars, the gravitational constant's not going to be your top priority. It's probably going to be breathing and not dying. Yeah? Okay. So here's a question. Mostly thinking B. Okay, please discuss. We'll vote again. They're okay. Yes, the answer is going to be B. Your mass is the same everywhere in the universe, because remember, the main difference between mass and weight is weight depends on all the gravity stuff that's happening, but mass is just the inertial measurement. And so what determines your mass?
Magnitude of the force of gravity.
That's what determines your weight,
Oh,
okay? The mass is actually, it's a much more fundamental thing. You're made up of what? Cells, which are made up of? Atoms. And atoms, remember, have a very specific mass, your atomic mass. So the number of atoms and what kind of atoms you're made up of determines your mass. And that doesn't change if you go to the moon unless you lose an arm or something. Yes?
Is there a way that you could measure the mass of yourself easily, or is that something really complicated?
Oh, it's really easy because you know what G is. So you take your weight and then you divide it by G.
Oh.
Yeah. That's a good question. So, when we're talking about gravitational force and weight, remember weight is the magnitude of the force of gravity, and mass is just what your cells are made up of, okay? So on Earth, we know that the force of gravity is mg. We can assume little g to be true, but it's basically big G times the mass of the Earth divided by the radius of the Earth squared, okay? Well, that's an easy thing to calculate, but you don't need to know that if it's a problem that's happening on Earth, all right? And you can also look, also Newton is 0.224 pounds, but I'm still right that it's close to the weight of an apple, although apples vary significantly from Fuji all the way down to small crab apples, okay? But just the average apple. Cool. Let's try this out. And E. We don't even have an E. Okay, try again. All right, the answer is B. And how do we come to that conclusion? Well, we have 10 kilograms, M, that's M. You multiply that by G, that's 9.8 times 10, and that's 98. All right. Okay, here's a second question. Just be wary of the units that you're looking at here. Okay, we got some A's, C's, and D's. We've got some A's and B's in the chat, so we will take some time, talk about this. We'll vote again. All right, more A's here. So yeah, that's going to be A. It's 10 newtons, and that's because, remember, it's asking the force of gravity acting on the force of, the cannonball that's given you the force of gravity. So once you have a force, you're already there. You don't need to do any math, okay? All right, so just weight, remember, is a force. Mass is not a force, okay? Weight is a force. So that means if you have different scales, this scale will give you mass in grams. This scale gives you force in pounds. It's a little bit tricky because they both use the same mechanism. This one is just converting back using G, okay? So neither of these are going to give you the right answer if you're on the moon. You'll have to recalibrate this. But remember, pounds are a unit of force, so you can only convert pounds back and forth to newtons, and kilograms are a unit of mass, okay? So 1 pound, that's about 4.45 newtons. All right, so remember, 1 newton is about the weight of an apple, okay? So about 0.22 pounds. And if you go the other way, 1 pound is about 4.5 newtons. That's okay. So here's a question. Let's assume that this is you, and I know this isn't probably most of your weights or anybody's weight really, but let's say you weigh 120 pounds on Earth at sea level. That's why we're at the beach. It's at sea level. What do you weigh on the moon? So the G for Earth, 9.8. G for the moon, 1.6. Yes?
So is 120 pounds equal to 120 newtons?
No. You don't necessarily have to convert. I would recommend using a ratio. If you want to know how many it is in newtons, 120 pounds is 534 newtons. Yeah. Yeah, like 20 pounds. Good job. Ratios. Ratios are your friend. But take a second to think about it. All right. We got 20 pounds here. Anybody agree, disagree? Yes. Do you have a question?
No.
Are you just waving?
No, I was just putting my hand up like I agree with that.
Oh, you agree that's 20 pounds. Okay, good. Like, hello. Okay. So the easiest way to do this is you know that weight is just mg, right? So whatever your mass is, you could calculate it by like doing the math and dividing by g and figuring out your mass here. Or you could realize that if you divide 9.8 by 1.6, you get about sixth? About 1/6? Yeah, about 1/6. So that means if you use the ratio, whatever your weight is here, you should weigh about 1/6 of that on the moon. okay? Because it's just mg divided by mg. So, ratios. All right. So you'd weigh about 20 pounds on the moon, or if you want to be real precise, 19.9 pounds, but 20 pounds is good enough for one lecture slide. And in both places, you'd be about 54.5 kilograms, which you could calculate too. Okay? So you and your friend that lives on the moon, yes, it's Elon Musk apparently, won 2 newtons of gold in a contest, and you congratulate them, and you say you also won 2 newtons of gold, but on Earth, and you want to know who has more money, or gold in this case. Okay? I'm going to start the timer while I eat my cookie. So you and your friend won 2 newtons of gold on the moon, and that was given to him on the moon. You won 2 newtons of gold on Earth. Who has more gold? Okay. Most of us think that our friend has more gold. Somebody keeps pressing E. The chat is pretty evenly split. So, okay, please discuss. We will vote again. Yes, although far less people voted, so whatever. All right, the answer is going to be B. Your friend has more gold. And the simplest way to think about this is, well, one, you know that things weigh less on the moon. So if you have 2 newtons of gold on the moon, you have how many newtons of gold on Earth? Multiplied by 6, so about 12, yeah. So you should have 12 newtons of gold on. If you take the moon gold to Earth, you get 12 newtons of gold on Earth. So the other way to do it is you can just divide by the g's that we know. So you can divide 2 by 1.6, and you can divide 2 by 9.8, and obviously bigger denominator means less gold, okay? So your friend has more gold, and if you answered anything but B, I have some things I'd like to sell you. Okay, on the moon real estate. All right, we're gonna try a problem. I'm gonna do this one for you, I guess. That's how this works. So hang on, I'm getting there. Okay, so we have an anchor hanging from a boat by a chain. This is a nautical problem. So the anchor has a mass of 50 kilograms, and we want to know the tension in the chain. Okay, so we'll draw our forces. What are the forces on the anchor? Tension going up, and weight going down. So if you want, we're going to stop doing all these free body diagrams eventually, but for now we'll just keep doing them. Oh, well, it's early. No? Okay. Every time somebody says I'm like, did I not show the slide on here?
I was wondering, does mg still count if you're in the water?
It's not in the water, but no. Well, actually, yes. But you have to, if you're in the water, mg still counts, but you have to add another force called the buoyant force that points up. So mg is still good in the water because you're still on Earth. Unless you get really deep, in which case the buoyant force is still a thing, and it's going to probably press down. No, it still points up, but it's very small. But what was it? If you go very deep, then G changes. That's the only other difference. Okay, sorry, big aside. So here is our free body diagram. And so if we sum up all of our forces in the y direction, that's going to be T minus mg. And what's the acceleration here? 0 is just hanging out, okay? So that's going to be mass times 0, which is 0. So that means tension is equal to the weight, which means that if we want to calculate tension, that's going to be 50 kilograms times 9.8 meters per second squared, and that gives us 490 newtons. So our tension here is 490 newtons. And we can make that pretty. Okay, simple enough. Let's try something a little bit more complicated. So here, let's say now the anchor is being pulled up at a constant speed of 2 meters per second onto a boat by a chain, and we want to know the tension in the chain. Okay, so I'll give you a couple seconds to think about that, and then I have a question for you. Okay. So is this in any way different from the previous problem? It is, right? You have a constant speed, but what do we know about, what does constant speed do to force? What, it should be the same, right? So we still don't have an acceleration, which means everything is exactly the same. So if we just copy and paste over here, we have the exact same solution for this problem. Because previously, what kind of equilibrium were we in?
0.
Static equilibrium, because we're not moving. Now we're in dynamic equilibrium because we're moving at a constant speed. But the key point is there's no acceleration still. Okay, so let's switch to something with acceleration. Now, the anchor is pulled up by a chain and is accelerating at a rate of 2 meters per second squared. And now we want to know the tension in the chain. So please calculate this. A lot of the things are the same, but this will not give you the same answer, okay, because now we have acceleration. So let's draw this out again. What are the forces acting on this thing? Anything different about that? The only thing that's different is acceleration, but tension is still up, right? mg is still down, but which way does the acceleration point? Up, because that's what it says. It's accelerating up, pulled up. So that means we draw acceleration here. And so if we want to draw our free body diagram, we can actually go back up here and just copy it. And the only thing that's different is we now have acceleration up, okay? But that does make a difference when we start writing out our forces in the y direction. So when we sum up all our forces in the y direction like we did before, we still have tension minus mg, but now it's not equal to 0. It's equal to mass, again, times acceleration, okay, which we know. And there's still nothing going on in the x direction, so we can just ignore that, okay? So when we solve for tension now, we have tension is equal to ma plus mg. We just do a little bit of algebra there, and we can say, well, that's mass times a plus g, or g plus a. So that's going to be 50 kilograms times 2 meters per second squared plus 9.8 meters per second squared. So is this getting bigger or smaller? Bigger. And that's going to be 590 because, look, 50 times 2, that should be 100. So we just add 100 to whatever we got before. Before we had 490 newtons. Now we have 590 newtons. So our tension has increased because of the acceleration. Okay? And hopefully this has some intuition that holding an anchor should be easier than pulling it up. Okay? From I don't know how often you're pulling up anchors, but just in case you have some experience with that. Okay? Any questions on this? All right. So let's talk briefly. I'm not going to switch back and forth because it's only one slide, about apparent weight. So remember, apparent weight is different from actual weight. So if forces are acting in the vertical direction, acceleration also plays a key. Now remember, mass times acceleration is sort of like a force. So for instance, if the anchor was like being pulled down at 2 meters per second, then it would feel lighter, right? Then the tension would be lighter. Okay? So there's a few different, apparent weight is sort of what a scale reads. So there's a few different times we've talked about when a scale doesn't read your actual weight. And what are those times? When it's on a slant, right? So when it's not parallel to the force of gravity. So if you put a scale on an incline, other times. Yeah, okay. Also, if you're accelerating up or down, right? So the best example of this is when you're a kid, or if you're me now, when you're in an elevator. What's the fun thing to do in an elevator, especially a really fast elevator? Like let's say you're in Vegas in an elevator. You jump. And when do you jump? Right before it accelerates, right? So when the elevator is going at a constant speed, does jumping do anything? No, right? So you have to jump right at the beginning or right at the end, because that's when the elevator is either going from stopped to a speed, which is an acceleration, or from a constant speed to stopped, which is a deceleration, right? And which one is the more fun one?
Deceleration.
Acceleration, going down, right? So if it's accelerating down, it goes from 0 to a speed. If you jump, it feels like you're floating because you end up staying up there and the elevator sort of moves out from under you and you're in the air for a lot longer. If you jump while it's going up, it kind of sucks because you end up like, it makes you feel like you weigh a little bit more. It's not fun. So anyway, that's the general idea with apparent weight. And so if you got on a scale in an elevator, right? If the elevator's not moving, it's going to tell you your weight. Right when the elevator starts moving, your weight's going to change. That your apparent weight is going to change. You're not actually weighing different, but the apparent weight is going to change because you're still on Earth. And then once the elevator reaches a constant speed, it should read your regular weight again. Okay? So when the elevator's starting and stopping, that's when your apparent weight's going to change because that's when you're experiencing acceleration. Okay. So we're going to do one example. Let's say you're holding a 10-kilogram bag of groceries in an elevator. How heavy does the bag feel when you are accelerating downward at a rate of 2 meters per second squared? And we'll do this one together. So let's draw this out. So here is your hand. It's not a good drawing of a hand, but whatever. And here's our bag of groceries. Okay. So there's weight, mg. There's also this force of your hand up. Yeah, I guess we could call that tension. Yeah, that's good. Tension. Okay, so it's very similar to what we were doing before. The other thing is we're accelerating downward now. So are you expecting this to be lighter or heavier in this case? Lighter, right? Because before we had when the anchor was accelerating upward, the tension was more, okay? So we're going to sum up all our forces in the y direction, and that's going to be equal to tension minus mg, and this is going to be equal to mass times acceleration, but which way is the acceleration? Yeah, so remember, if this is the y direction, this will be negative acceleration, okay? That's very important, and we see that from looking at this versus this. Okay? So when we calculate our tension, we end up with mg minus ma, which means tension is mg minus a. So our mass is 10 kilograms. We know g is still 9.8 meters per second squared, and then this is minus 2 meters per second squared. So that's going to be an apparent weight of 78 newtons, whereas the total weight of the bag, right, is going to be 10 times 9.8, which is 98 newtons. So it will feel lighter. So 78 newtons. Okay, so that's how heavy it feels. Any questions on that? All right. And we just talked about this. So we'll just discuss this just in the interest of time. So if you weigh yourself in the elevator, when do you feel, when is your apparent weight heavier and when is your apparent weight lighter? So let's say you're going at a constant speed. What's your apparent weight? The same as your normal weight. What if you're accelerating upwards? You feel heavier. What if you're accelerating downward?
Lighter.
Hey, you guys are killing it. All right, perfect.